Hello, and welcome to part 1 of lecture 24, covering sections 10.5 and 10.6, which are the end, or nearly the end, of the chapter on rotational motion, or the second chapter on rotational motion in Young 14th edition. The topic here is angular momentum. In this lecture, we're going to introduce the basic concept of what angular momentum is as a vector, what it physically represents, how we calculate it. In part 2 of this video, you're going to see how to work with conservation of angular momentum as a tool for solving problems. And in part 3 of this lecture, you're going to look at one particular application of angular momentum and torque, which is gyroscopic motion. All right, so let's get into this. All right, so first I drew a picture over here, which shows angular momentum as a vector. And we represent angular momentum as L. Okay, so it's L as a vector is really reserved for angular momentum. It's the letter you're going to see. All right, and angular momentum is defined as a cross product. So there's two ways to multiply vectors, cross products and dot products. Cross products are when you multiply vectors and the result of that multiplication is itself a vector. And that's what's happening here with angular momentum. We're multiplying a moment arm vector and a translational momentum vector and getting angular momentum as the product of that multiplication. Okay, so we see, right? So if we have the moment arm, and the moment arm here just represents the displacement. I should really probably call it the displacement vector to be more general, but the displacement from some origin of your choice, okay, that's the origin that the angular momentum is relative to the point where your mass is located, okay? Now that could be your center of mass, okay, or it could be the mass of a particle, in which case the center is also the entire mass. Then we have the translational velocity vector. Now the translational velocity vector would be parallel to p because translational momentum is just mv, m is just a scalar, so then your p vector is going to point in the same direction as your velocity vector, and it's just going to be longer, right? Okay, or shorter, I suppose, if m is less than 1. And then when you do the cross product, one way to confirm that in this case, angular momentum would point along the positive z-axis if the displacement vector points along the positive x and the velocity vector points along the positive y. One way to confirm that is to hold your thumb in the direction of the displacement vector r, hold your index finger in the direction of v, okay, this has to be your right hand, so have your thumb pointing in the direction of r, have your index finger pointing in the direction of v, and then your palm is going to point in the direction of L. In this case, out of the screen or out of the board, out of the page, straight up in the positive z direction. That's the right hand rule, which is a way of confirming the direction of any cross product. In this case, a cross product giving us angular momentum. Okay, so there you have it. That's how we define angular momentum. Why do we define angular momentum that way? Well, it makes sense for it to be a cross product because it's got to be a vector. Furthermore, it's got to be relative to some origin because it's an angular phenomenon, so it's got to be pivoting about some point. It may not be making a full rotation, right? So you can have angular momentum as something that is certainly not rotating. It's never going to make a revolution, but as long as it's pivoting relative to some origin, some pivot point, right? Then that's it. That's technically a rotational quantity, okay? Unit-wise, if we think about it, right? It has units of kilogram meters squared per second. Okay, well that's a lot like joules, right? The only difference is it's not seconds squared. Okay, you can see where those units come from, right? Because obviously translational momentum is kilogram meters per second, and then we just have an extra meter. And if you think then, angular momentum becomes joule seconds. In the same way that I think the most evocative unit of translational momentum is a Newton second, you can see that just having that extra meter gives joule seconds as the units of angular momentum. All right? So there you have it, the definition of how to calculate it, where and units and so on. Okay, so good introduction, I hope. Furthermore, since as I said before, since translational momentum is just mv, we can pull the scalar quantity out of the cross product and just have it leading in front. Okay, so that's an important thing about cross products is that r cross p is not the same as p cross r. Right, they are not equal to each other. The order matters. Cross products are 100% not commutative, and you could confirm that with the right-hand rule. You can confirm it with just calculating them using the formula for cross products. Absolutely the case. Good thing to remember, right? In fact, it's equal to the negative of p cross r. But one thing you can do is you can pull the scalar out, right? Other thing, prove it for yourself. Okay, So there we have the moment arm, translational momentum, everything I mentioned. Okay, so looking down, I'll get to this in just a second. So actually here, yeah, so we'll leave that. But if we look at this next line, all I'm showing in this next line is just the magnitude. That's it. It's just the magnitude of the angular momentum. And there's a number of ways to think about it. We can think of it as RMV times sine of phi, where phi is going to be the angle between V and R, right? So here I have that when P is perpendicular to R, and again, I'll get back to this in just a second, but when P is perpendicular to R, then angular momentum is maximum magnitude. Because again, phi represents the angle between P and R. So if phi is 90, then sine of 90 is 1, and then your angular momentum would just be this. It would just be RMV. That's the biggest it can be, okay? All right, so again, angle between P and R, or angle between V and R, depending on how you think about it, because P and V are always parallel to each other by definition, okay? And furthermore, there's just a few ways of thinking about kind of what component we're looking at. So the way I drew my kind of example here, my nice way to demonstrate the right-hand rule and to really illustrate what angular momentum looks like in a 3D coordinate system and so on, well, it was pretty idealized because R was entirely along one axis, V was exactly perpendicular. What about if V is off to the side, right? Well, if V is this way, then you only care about the component of V that's perpendicular. So in that case, you multiply R and the perpendicular component of V. Okay, so that's what I'm saying kind of over here, right? But, likewise, well, that's V relative to R. But maybe V is the axis that I want to pay attention to. Well, in that case, I care about R that's perpendicular to V. So it's all kind of just relative to kind of which of your vectors you choose to be your axis direction. Because it makes sense. Just like when we had all our examples of blocks sliding down ramps, it always made sense to have a coordinate system where we had to take as few components of vectors as possible. Same thing here. We're going to choose one of our axes to point along one of our vectors given an option. Okay? All right, so there we have it. Angular momentum, cross product definition, magnitude of angular momentum, thinking about what components to take, okay? Or the angle between R and V, and just taking sine of that angle, which is, of course, this definition of cross product. All right, so that out of the way. Important first step of thinking about what angular momentum is. Now, the other big role, one of the other big roles angular momentum plays, is in redefining Newton's second law. This is the fourth and last time we'll see Newton's second law in this class, and this is Newton's second law in the angular momentum form. So it's a rotational form of Newton's second law, but instead of it being tau equals I alpha, which was the angular acceleration version of Newton's second law, it's tau net, importantly, okay, equals the first time derivative of angular momentum, okay? So you can really compare this to F equals dp over dt, right? We saw before, this was the second time we saw Newton's second law, because the first time was ma, but the second time we saw it was as the first time derivative of translational momentum, right? That was Newton's second law, right? And it turned into, then we could show that was equivalent to ma, but sometimes it made sense to think about momentum rather than acceleration, right? Depends on the system, depends on what we're given, depends on how we want to solve it. Okay, we have different tools in our tool belt. All right, so this is it. This is Newton's second law yet again. Down here, I just quickly show that we could then define torque, net torque here, I'm leaving off the subscript, as, by definition, Newton's second law definition, dl over dt, okay? I guess more by theorem or by law. And then I want to show that it's equivalent to tau equals I alpha, the most recent, and the third out of fourth time we saw Newton's second law. Well, then all I do is I say, okay, well, then I'm going to replace L with I omega. That's kind of interesting. Why didn't I replace L with what I had up here? Why don't I replace it with RMV sine phi, right? How do I come up with I omega? Well, it turns out that RMV sine phi for solid objects becomes I omega. I'll leave the proof out of the lecture. I didn't assign in the homework anything, but certainly you can kind of see where that comes from. I mean, thinking about like how I is calculated, how it's the sum of moment arms of each little mass element, and how all their effects then total up the moment of inertia. You can then kind of imagine how R, M, and sine theta become I, and then you're going to be combining that with V and R, at least another component of R, to get your omega, okay? And so the overall fact is that for solid objects, L is equal to I omega, okay? I'll get back to the vector definition of the directionality of that in just a second. But here, if we just care about this, the quantity, the units, which check out, check them for yourself, then that's a nice definition. And it's going to be one that comes up a lot, because a lot of times we are dealing with solid objects. And it also quickly shows that this version of Newton's second law becomes this version of Newton's second law, because then we can say, oh, well, if I is independent of time, okay, which is usually the case, then you can pull I out of the derivative, and then you just would have I d omega dt, which by definition is alpha, because the first time derivative of angular velocity, of course, is angular acceleration. Right? So just kind of a good review of kind of the units we've seen and the quantities and so on. Okay. So then, anyway, the last form of angular momentum, the one that's specific for solid rotating objects, those would be those rigid, i.e. solid objects, fixed axis, the kind of the rules that we use whenever we have a well-defined moment of inertia and so on. Well, it's L equals I omega. Well, why would it be, in other words, like the vector thing I said I would just mention in a minute, why would L point in the same direction as omega? How can we be confident about that? Well, it's one thing I can argue by analogy is that, certainly there was no stretch of the imagination that momentum and velocity point in the same direction, since it was all we were doing was just multiplying, the vector by a scalar. In that case, we're multiplying the vector of velocity by m in order to get momentum. Well, same thing here. We're just multiplying angular velocity by a scalar to get I. And notice that the parallel is perfect, right? It's instead of P equals mv, now it's L equals I, rotational mass, i.e. moment of inertia, angular velocity, omega, right? Instead of translational velocity v. Great, okay, it all makes sense. And so it also tells us if I have like some spinning disk, and I have angular velocity that points up like this, well then angular momentum would point along that same axis. It would also point perpendicular to the plane of rotation along the axis of rotation. Okay? And in that case, I could still use a right-hand rule or a simpler version of it where I curl my fingers in the direction of rotation. So just like the picture I drew, I would curl my fingers in the counterclockwise direction. My thumb would point up out of the page, telling me that's the direction that both angular momentum points and angular velocity points. Okay, so that's the introduction. Okay, here we have a table that just summarizes all the familiar terms for translational momentum. Force, linear momentum, all right, linear momentum for a solid object, linear momentum for a solid object with a well-defined center of mass, Newton's second law in momentum form, translational momentum form, and then finally the idea of conservation, that P is a constant. So the total sum of momentum vectors for any system is constant as long as the net torque on that system, in this case, the net force on that system is zero. All right, so that was our big rule for conservation of translational momentum. All the same stuff applies over here to rotation. Okay, so we have, instead of force, we got torque. Okay, instead of angular momentum for a single object, we use L. Notice here we have lowercase and lowercase. That's kind of typical if you're talking about a particle. I tend not to use that because I want to use L for lengths. So I'm going to shy away from using lowercase l, but you still see it come up. You can at least usually tell that it's going to be angular momentum because it's a vector rather than just a scalar quantity. But sometimes it's got to be context, right? And it's just kind of the imperfect system of having variables that serve double purpose. But anyway, here we have translational momentum for a system, angular momentum for a system, right? The sum of particles. Here we have what I was saying, angular momentum for a solid object. Here is Newton's second law in angular momentum form. And then finally, conservation of angular momentum. But instead of saying that we want the sum of external forces to be zero, we want the sum of external torques to be zero. So torque net needs to sum up to zero. All right? But the analogies are all here, right? Everything that had a definition, every kind of common theorem, every common formula that we saw in translation now has its parallel over in rotation. Every single one of them. And this really kind of seals the deal, right? Because we've seen tables like this before. I put one table in the last set of notes. And we saw, all that. It was up through all of kinematics, through forces, through work and energy. Those all had exact analogies in rotation. And now we're showing that indeed momentum is no exception, okay? But as I said before, everything in rotation is slightly more complicated, right? Every term that was just kind of like one thing. Force was just a force. You just kind of had to know, how big it was and where it was pointing. Well, now we need to know how big it was, where it's pointing, and where it's located relative to a defined axis. So there's always that one extra bit of information, sometimes two. So everything about rotation has that extra intricacy to it. Okay? Analogies, yes, but equal level of complexity? No. Increased level of complexity. Always be aware of that with rotation. Don't be blindsided by the extra bit of information that is built into rotation. All right, so let's do some examples. Okay, so in this, in example 1, I'm going to cover part A and I'm leaving part B for practice. I'm gonna get this something out of the way. There we go. All right, line that up. There we go. Okay, so first thing I'm going to do is draw the picture. Okay, well, let me read the problem. Okay, so suppose a position vector r is in the xz plane. Okay, so that would be this plane. Right, this is the xz plane, like that. Okay, and it is given by the following vector in I hat, j hat, k hat notation. Of course, there's no j hat; it's 0 because it's left off. And then what is the angular momentum at the origin of a particle moving with the following translational velocity, right? So translational velocity is entirely in the x direction and is negative, right? So it's pointing in the negative x direction. So I drew the picture, okay? So here's the p vector pointing in the negative x direction as specified, okay? Here's our r vector that has components of z and x, but no component of y. So it's in the xz plane, as it said, okay? So what does that mean then about angular momentum? Where will angular momentum point? Well, angular momentum, since both P and R are in the same plane, angular momentum is going to have to point perpendicular to that plane. No surprise there. I think solid rotating object, that angular momentum points completely perpendicular to the plane that composes the object. Okay, so that means that L is going to point, it turns out, in the negative y, circled z, but it's going to point in the negative y direction because there's an axis here that goes straight down, and that's the negative y axis. Okay, we can come up with that with the right-hand rule because we could think about, some component of R that's perpendicular, right, to P. That would be this one right here. And so I could literally then just multiply the perpendicular component of P by P itself. Well, let's look over here. Okay, so the perpendicular component of P would be the Z component. So I'd have 1.4 and I multiply by negative 10. So then my angular momentum should have a value, a magnitude of 14. And it should be negative 14, and it should be entirely in the y direction due to the right-hand rule. So literally, we could do it with almost no computation, okay? And it's good to have that as one way to approach this problem. But I'm going to show you the way you can just come up with that, you can confirm your skills as you build more confidence using the right-hand rule, build more confidence quickly thinking about components by just going through, using the formula for the cross product, and just getting the answer by following the steps. So let's see what that looks like. Okay, so the formula for a cross product, I always base it off of this, what's called a 3x3 determinant. It's just a useful way for me to remember where the formula comes from. You could also just have the formula out in front of you. The one that basically says that it's going to be rypz minus rzpy on the I hat minus rxpz minus rzpx on the j hat plus rxpy minus rypx on the k hat. So that's always the rule. That's the way you can always look at it and remember you're doing it right. Okay, you can just have it in your formula screen or on a computer screen. Okay, so here it is. Okay, so here's the three terms. Right, here's the whole term that comes from that, or is attached to the I hat direction, the x direction. Here's the term that has the minus in front of it because it's the odd one out. It's the j one. I always think of the odd one out because it's the one that's split. All the other ones you can make these nice kind of cross hatches like that. Okay, and that one, okay, is all attached to the j hat. We'll talk about why there's 0 in just a second, but you can probably see why. And then this one here is attached to the k hat, although I left it off. Okay, and then you go through those steps and you're like, oh, well, you've got a lot of zeros here. Like momentum doesn't have a z component. Momentum doesn't have a y component. Remember, that's translational momentum, only has an x component. Likewise, right, momentum doesn't have a z component. Oh, here we got something that's non-zero. All right, finally. Over here, again, we've got momentum. Translational momentum doesn't have a y component. Over here, oh, well, translational momentum does have an x component. But there's the one component that ry doesn't have, okay? So when you do that, you end up only with the term on the j hat, okay, which again, the right-hand rule told us that it should be, and the quantity ends up being negative 14, because we got negative and negative and a third negative, which ends up being negative times negative times negative, comes back to a negative. So negative 14, magnitude, units, joule seconds, direction, j hat, okay? And the negative tells us is pointing down in the negative y direction, okay? All right, so that's the approach. Again, I left off a k, I'll put that on before I upload it. But that's it, that's the whole thing. That's the approach that you would do for a problem like this. Or two alternative approaches, kind of come up with very little work, components, right-hand rule, or, hey, just follow the formula, check your work. All right, okay, so hopefully that makes sense. Part B would be good for practice. All right, so number 2, same sort of thing. It's going to be very focused on vectors and a particle, not a solid or anything here. But I'm instead going to give us an approach that requires us to think about torque as well. Okay, so we're going to have a time-dependent position vector. That's going to allow us to come up with a time-dependent velocity vector by simply taking the derivative. You'll see in just a moment. And then from there, we can come up with angular momentum by taking the cross product. And then once we take the cross product of r and v times m, then we can take the derivative of that new vector to get torque. So it's simple as that, isn't it? Okay. Now, could we have just gotten torque by just taking the definition of torque as basically, could we have done torque equals r cross f? Well, sure, because then it would be r cross m times a, and we could have gotten a by just taking the second derivative of the position vector. Now, I don't take that approach, and so and if that you want to kind of look into that or need some more details on it, ask me about it, absolutely. But it's they're all just all the same idea, right? It's these theorems are very much interrelated. Okay, they're not independent of each other. All right, so here's the picture. Why does it look like this? Well, because here's our position vector, right? It's time dependent. What does that mean, right? Well, time dependent position vector means that this position is growing linearly in the I hat direction, the x direction. It's actually started off with a value of 4 in the y direction, the j hat direction, but then it's falling off parabolically. So it's falling off in that direction. So I'm going to get into the negative y. Meanwhile, it's growing in the positive z direction. Well, here you have it, right? Here it is, starting off. That's the only term that starts off as non-zero, because if you plug in t equals 0 for the k hat and I hat, you just get 0. But if you plug in t equals 0 for j hat, you get 4. So that's why it starts right there at t equals 0. And then here you see, right, growing linearly on z and x and falling off. It's supposed to look like it's falling off and falling into that plane, eventually passing through the xz plane and continuing to descend in the negative y direction. Okay? So we should expect the angular momentum to point this way. The angular momentum should point in the xz plane, and it should have components of both x and z. Why is that? Well, because it should be perpendicular to this parabolic path. Because this parabolic path essentially represents the plane of rotation. And so the angular momentum should be perpendicular to that plane of rotation. Now, its length is going to be time dependent because this is not a circle. If this was a circular path, and we're going like this, then angular momentum would be perpendicular to that circle and it would just have a fixed value. But here, this is definitely not. It's parabolic. It's going to go faster and faster and faster and faster. Okay? All right. Meanwhile, torque will also be in the same plane. It will not point in the same direction, and it too will be time dependent. Let's show it. Okay. So, as I said, one of the first things I'm going to do is I'm going to take the information I was given for the position vector, take its derivative, which gives me the velocity vector. I'll need that. Okay, I'm going to be using this definition of angular momentum. Okay, so again, just like in the problem above, I'll write out the 3×3 determinant. Remember to take care of everything I need to. Here, since I have v, I explicitly have the m in front. Before, I was given a value of p's, if you see up here, right? That's why those were all p's instead of v's, and I didn't have to have an m in front. All right, so I go on and actually write out the formula, right? Now I'm going to find out which ones are zeros, okay? Well, it turns out everything attached to the j hat is 0. And that's it. Otherwise, everything survives. I do a lot of simplification here, right? So there is, they didn't come out as just 4.8 t squared, but check your work. Make sure you get the same thing. I've double checked it. All right, and then eventually it simplifies to this by distributing the point 2. Okay, so we can see that, as I said, the angular momentum has a x component and a z component, and its exact direction is going to be growing with time. Okay, so the angular momentum is going to grow quickly. It's going to not always point in the same direction, but it will always be in that plane. Okay, and always be in this quadrant of that plane as well. But it will gradually, let's see, which one's growing faster? So it's going to grow. It's going to gradually point more and more towards negative z. So over time, the angular momentum is going to get longer and more towards negative z. Okay, all right. So that's pretty cool. Now let's just take the derivative of this vector function in order to get torque, the time derivative that is. So that's all I do, right? I pull the point 2, or I leave the point 2 really out in front. So I do the undistributed case. It's easier to deal with numerically. And I'm just going to take its derivative, all right? All right, and I do that. So I take the derivative. For example, this would become 2 times 4.8, so 9.6t. This would just become 0. This over here would become negative 12t. that would also just become 0. And then all I do is just distribute the 0.2. So when I distribute the 0.2, I just get 2 linear values. Okay? So same sort of thing here with torque. It's time dependent, but interestingly, it's not going to grow as dramatically as angular momentum. It's linear. And that, of course, makes sense, right? Because if your angular momentum is proportional to t squared, your torque better be proportional to t, because, of course, it is the derivative of it, and specifically the derivative with respect to t, time. Yeah, and it's going to be in that same quadrant, same sort of quadrant, positive x, negative z. And what's going to happen is it's also going to become, it's going to point more in the negative z direction, but it's always going to be proportional, right? Because if I double time, then these values being linear means that it has a fixed proportionality. So it will always point in the same direction, okay? It will always point in the same direction, whereas angular momentum will not. And that's kind of fascinating, right? Because you could find the angle between them, and the angle between them would be time dependent. Okay, food for thought. Okay, so there's another example, similar, but kind of maybe more robust than example 1. All right, so I got one last one to show you. Okay, so example 3, solid object. Okay, finally, not a particle. It's the only one in this set of notes. You're going to see a lot of stuff with solid objects when we focus on conservation in part 2 of this lecture, lecture 24. What's going on with this example? What's kind of the takeaway I want you, before we start it? Well, really, I'm going to show you an approach that in practicality you wouldn't use that often because you could use energy, and we're going to check our work by using energy. But it's so important as sort of a kind of a demonstration to really show, hey, look, you can use angular momentum, and you should be able to get the same results. Because obviously, thinking about angular momentum, thinking about this, this velocity that's changing as the torque is changing, all those sort of ideas have to be related to energy, because energy is being conserved while momentum is being conserved in some systems, isn't it? Right? Now, you might have a system where energy isn't conserved and angular momentum is. Okay, that's collisions, and that's why we will focus a lot on collisions, because they're such an important example of a system where you have one thing is conserved and another isn't, and then you can find out the fact that angular momentum is conserved to find out exactly how much energy was lost, right? But here both things are. Both angular momentum and energy are conserved, because it's a falling object, okay? So let's think about it. What's going on here? And let me think about this. Let me phrase this a bit differently. So, it's not even so much that angular momentum is conserved. That's not the point. I think I was focusing too much on kind of that. We tend to use that as a problem-solving technique. It's not that angular momentum is conserved in the system. It's that we know exactly the rate at which it's changing, because the torque is well defined. We know we can exactly calculate it. We can find out. So in fact, there is an external force, gravitational force, and it's even a time-dependent force because it's angular. Okay, think pendulums. That's really a pendulum problem, right? But a pendulum that started upright. And since we can then find out the rate at which angular momentum is changing, then we can relate it to energy, which is in fact conserved. Okay, so backtrack on what I said. Clarify one last time. This is a system where external torques are not equal to 0, so we should not expect angular momentum to be conserved. However, we know exactly what that external torque is. We can use that external torque, find out the change in angular momentum, find a particular value, I'll say what that is in a second, then show that that is a value we could have found of conservation of energy, to say, hey, why didn't we just do it that way, I suppose, but also to show that the theories, they support each other, okay? All right, so radio transmitter tower has a mass of 80 kilograms, 12 meters high, okay? So the 12 meters is this length here, right? That's the 12, okay? The mass, right, that's the M, it's 80 kilograms. All right, so the tower is anchored to the ground by a flexible joint at its base, but it's secured by 3 cables 120 degrees apart, as shown in the figure. If one of the cables breaks, then the tower would fall away from the broken cable, rotating about its base. What would be the speed at the top of the tower as a function of the rotation angle, okay? So the idea here is that we actually don't care about them being 120 degrees other than to know that they were evenly spaced. And we know there's going to be some plane halfway between these 2 cables where it's going to be falling exactly in that plane. Okay, so that's kind of the only thing you care about, okay? So we're taking a slice here in 3D space, and the rotation is entirely in that plane, okay? Okay, so enough about that. Let's get to the parts that matter. What would be the speed at the top of the tower as a function of the rotation angle, theta? Okay, note, start the analysis using the definition of torque, using Newton's second law, okay? And approximate the tall rod of uniform density, okay? Or as uniform density, all right? There we go, all right. And that's kind of part A. I didn't put an A in there. That part right here, that would be A. And then part B, show that these results agree with those obtained using conservation of energy. All right, so how do we do this? Okay, so we write Newton's second law in angular momentum form. Okay, then I write that the torque itself, this is, of course, there's torque net, in this case, it's not equal to 0. It's just equal to the gravitational force times the perpendicular component of the displacement vector. Okay, so here's the displacement vector from the pivot to the center of mass, because the gravitational force only acts at the center of mass. Okay, so then the perpendicular component is our moment arm. Now the moment arm is going to change as theta changes. It's going to change as it falls. Oh, that's fascinating. So that's actually saying that r perpendicular is a component of theta. Okay, we'll come back to that. Okay, and then we're going to take angular momentum, all right? And since it is a solid object, we're going to use this relationship right here, which is how I was able to relate dl over dt to I alpha, right? So refer to 2 pages back for that. Okay, there you have it. All right. We're going to take the moment of inertia as known. It's just 1/3 ml squared. Okay, none of those things are changing. The mass isn't changing. The total length is not changing. I know I said that the moment arm is changing. It's a function of theta, which means it's a function of time as well. Not that we know what that relationship is, but it's changing, non-constant. But these things are all constant. Okay, so they're going to come out of the time derivative. You'll see that in a second. Okay, so then we'll get back to just dealing with that time derivative. We'll relate it back to torque in just a minute, but let's clean it up a little bit. So there's our time derivative, dl over dt. Okay, the L just becomes that, because remember I was 1/3 ml squared. Look that up from a table of moment inertias or prove it using calculus. Omega is just the definition of angular momentum of a solid. Okay, so then all those constants come out. Omega doesn't. Why would omega not come out of the derivative? Well, because it is time dependent. Okay, because omega means, well, if you think about things that start to fall, they fall, slowly at first, an object that started off vertical, and as it tips, it's going to speed up as it falls. So that's common sense. But of course, it has to speed up because it's going to be related to the torque. The torque is, even if the torque would have to be 0 for omega to be constant, it's certainly not. And in fact, the torque itself is not even a constant. It's changing. And so then omega definitely is going to have to be time dependent. Okay, so this is going to stay inside the derivative. So now we'll go back to Newton's second law. Okay, I'm going to rewrite torque now as mg r sine theta. Okay, now r sine theta is just a rewriting of r perpendicular, which is in the figure, and the equation above, or the line above. Okay, but there's a reason I want to write like that. Okay, and then we've got our dl over dt cleaned up a bit. Now we're going to do a dirty little trick. Okay, so this is something that comes up a lot. It's called multiplying by 1. Because obviously I can take an equation and I can multiply both sides by 1 and not change the validity of that equation. We all absolutely agree. But sometimes you can multiply by 1 in a way that's a little obfuscated, that doesn't look like 1. And that's what I'm doing right here. Okay? I'm going to multiply by d theta over d theta. Okay? Now I'm doing that to both sides because I have to. But over here I'm just going to say, well, d theta over d theta is just obviously 1. But here I'm not going to do that. Instead, I'm going to take the d theta over d theta. Okay? I'm going to put the 1/2 of it, the denominator, under the d omega, right, which is already there, and I'm going to put the other d theta on top of the dt. So what I've done is I've done a differential substitution by multiplying by 1. Okay, why would I do that? Well, that means then I can rewrite d omega over d theta. Okay, so I can kind of leave that as my derivative. Now I'm taking the derivative of angular velocity with respect to theta. Well, that kind of makes sense because that is, after all, what I wanted, right? I wanted speed. Now, speed implies translational velocity, but I can just use v equals, omega r. Okay, remember v equals omega r? I can use that to find the speed of any point, okay? But I wanted that as a function of theta. Well, here I have a derivative that's kind of leading me towards the thing I was asked for. That makes sense. And now I've got omega. Where did the omega come from? Well, it just came from d theta over dt. By definition, that's angular velocity, because that's the instantaneous change of angular position with respect to time. Angular velocity, omega. All right. So now that we've done our differential substitution, we'll do a couple things, okay? So remember, this is the moment arm, the component of the displacement vector. Well, the displacement vector is exactly L over 2, because it's a uniform density rod, so the center of mass is exactly in the middle. Now again, sine theta changes, but the r being L over 2 does not. Okay, here is my new d omega over dt, rewritten as d omega over d theta times omega. All right. Now I'm going to do something we've seen a lot when we need to solve an equation like this, by direct integration is we make sure all the things that are a function of one variable are on one side, and all the things that are a function of the other variable are on the other side. In other words, the variables match up with the differentials. Okay, so that means all I need to do is multiply both sides of this equation by d theta. Okay, that means they'd cancel on this side, and then I'd be left with just d theta on the left-hand side. Well, that's good because I got sine theta. Okay, good. That means I can actually integrate that with respect to theta. And then meanwhile, I got an omega d omega. Okay, so direct integration time. Okay, so the left-hand side, I'm going to be integrating with respect to theta. Okay, I'm going to integrate from 0 to theta, right? Because the initial angle is 0. You can see, right? It's defined this way. So when it was vertical, it had a theta of 0. Theta is going to grow. It's only going to grow up to pi over 2 or 90 degrees because then it's going to hit the ground, but we'll still have it grow up to some final value. All right. So lower limit 0, upper limit a variable. Likewise, when it was vertical, it was at rest. So lower limit 0 with respect to omega, and then final omega is just going to be omega because we want to leave it. We don't want to get a function out of our integral. We don't want to get a number out of our integral. Every time you want a function through direct integration, you want your upper limit to be a variable. Okay. All right. So then I go through and I just do some rules of antiderivatives. Right. My sine theta is going to become negative cosine, and then I evaluate the upper and lower limits, and I'm left with 1 minus cosine theta. All right, makes sense. Okay, and that's actually also after switching the order because the top one's a negative, and I don't want the negative to be. It'd be really negative cosine theta plus 1, but I rewrote it as 1 minus cosine theta. All right, and then over here, my omega is just going to become omega squared over 2. All the 2 times 3 becomes a 6 in the denominator, and then I evaluate my limits. Nothing really interesting there because it's a 0, and a function like that just would be 0 at the lower limit. And then I just solve for omega, and there we have it. It is omega as a function of theta. Okay, that's a neat result. Okay, and then I was asked for the velocity at the tip though, so I'm just going to use that v top or tip is omega times L because it would be the full length from the pivot. Okay, because that would be a distance, right? That's the L. All right, so then the velocity of the tip of the falling rod is we just have that extra L. It was if I bring it inside of, because I'm multiplying omega, remember this is all omega, if I'm multiplying it by L, I can bring the L inside the square root, it becomes an L squared. That would cancel with the L in the denominator, leaving 1 L in the numerator. All right, so there's my result. Looks good. Now, what if I plug in particular values? Well, one value I could obviously plug in is 90 degrees. 90 degrees would be once the rod is fully fallen, it's hit the ground, it's horizontal, okay? The radio tower is fully fallen. Okay, well, cosine of 90 degrees is just going to give me 0, and so then I would just have the square root of 3GL. So that's the one I'm going to confirm is the same result we get with conservation of energy. Okay, so for conservation of energy, it'd be rather simple comparison, just the gravitational potential energy of the center of mass, got to be the center of mass, otherwise you don't get the right number, equal to 1/2 I omega squared. I is relative to the pivot point. The pivot point here is going to be the end of the rod, so I have to use 1/3 ml squared. All right, well, I do that. There we go, right? I rewrite h comma as L over 2 because it started when it was, the rod was positioned vertically, so the center of mass would have been a full L over 2 above the ground. All right, and then there we go. That's the velocity, and that's the velocity once all the potential energy becomes rotational energy. Is there any translational energy? No. Now there's translational energy of little individual parts of the rotating object, but when I want to make that conversion, I want to then find omega and then use V equals omega L. Here I do it kind of a one step because I replace omega with V over L. But if I had been interested in the translational velocity of the center, it would have just been V over L over 2. As simple as that. Okay. But anyway, it checks out. I get the same result with rather complicated Newton's second law, angular momentum, as I would with rotational kinetic energy related to gravitational potential. All right. Pretty cool though. Okay. All right, so that concludes the last example of the first half of Lecture 24. Please check out the later parts of